Тогда я
Хорошо.
все.
Okay.
Одной
So,
проблемы.
dear participants of European Non-Associative Algebra Seminar, today we have a talk by Vladimir Gorbatsevich from Russian State Technological University named after Tsiolkovsky. The title of his talk is on some classes of basis in finite-dimensional algebras. Please.
Okay, thank you. First of all, I want to thank for inviting me to this conference. I am going to speak about Lie algebras, ordinary Lie algebras, finite dimensional, over a field of characteristic zero, mainly real Lie algebras, sometimes complex Lie algebras, and without any geometric structure. In some sense, it's classical Lie algebras. But for such Lie algebras, I want to consider some special kind of basis. And and moreover, I am going to speak not about general Lie algebras, but mostly about nilpotent Lie algebras. Why? Because from my point of view, nilpotent Lie algebras is a very strange object. It's very easy to define them. It's very easy to prove some initial properties as Engel theorem and so on. But if you want to understand the variety of all nilpotent Lie algebras, we will find that it is impossible to understand it. Some special kinds of nilpotent Lie algebras are investigated, but now for nilpotent Lie algebras, we have some unresolved but very easy and simple problems. I mention only one of them. It's a problem of rigid nilpotent Lie algebras. We know that any semi-simple Lie algebra is rigid. It means that there are no non-trivial deformations. It's rather easy to prove now. It is known that for solvable Lie algebras, some of them are rigid, while some of them is not rigid. And if we ask such question for nilpotent Lie algebra, the answer is we don't know. So, from my point of view, any attempt to investigate nilpotent Lie algebras is useful. And now I'm going to speak about some special basis. I started with some general definitions. Let A, I'm sorry, I don't want to write now. Let B I don't understand what it means. Okay. Let A be some finite-dimensional algebra, not necessarily Lie algebra, but finite-dimensional over a field of characteristic zero. And let EI is some basis. There is a notion of multiplicative basis. It is the basis for which any product is collinear to some basic element or equal to 0. I prefer to speak only about the cases when there is a real proportionality. Such algebras are called multiplicative. There is some extreme variant of the definition when not only proportional but equal any product equal to some basic element. And some investigations about the general case are known. For Lie algebras, some years ago, one other variant of multiplication algebras was introduced. It was done at 12 years ago in the article of Laure and Will. The name is Einstein solved manifolds. This is mathematical analysis, with mathematical annals, volume 3, page 190. This notion was introduced when considering Einstein metrics on Lie algebras. Then this and such algebras, I give a definition some later, are called nice bases. The definition is the follows. Some basis is called to be nice if for any unordered pair of indexes, AG, its commutator is proportional to some basic element, but some additional property. If some index k corresponds to two such pairs have to be disjoint, so as non-ordered pairs. Such bases are called nice bases, and nice bases are closely connected with investigations of Einstein metrics. In this direction, I propose to introduce some more special kind of basis. I name it beautiful basis. We have nice bases. Maybe it's possible to consider beautiful basis. In this case, the number k, for any number k, the unordered pair Ig is defined uniquely. It's some variance of bases. Why such bases are useful? I know two reasons for it. First of all, if we want to consider some special examples, when we consider multiplicative algebras, Lie algebras, in this my talk today, it's very convenient to define them. Because if we have a Lie algebra, when this commutator is a linear combination of many basic vectors, it's rather difficult to understand the structure of this algebra. But if this commutator is zero or proportional to other basic element, it's very useful. It's very useful to understand the structure of this algebra. And the second, about calculations, using some symbolic calculations with Lie algebra. If we have multiplicative basis, it's very easy to define for any symbolic computing this algebra. So there are some reasons to investigate such algebras. The structure of nilpotent Lie algebras having a nice basis was considered later in details. Some geometrical structures on the corresponding algebras were described. About classification, the nilpotent Lie algebras of dimension 9 up to 9 having nice bases were listed. Beginning with dimension 7, there are infinite families of such Lie algebras. But for dimensions less or equal to 5, it is easy to describe nice bases, and it is easy to verify that any such nilpotent Lie algebra has only one nice basis. For dimension 6, it's a very interesting situation. It was found that there are two different, in some sense, two different sorts of nice bases. But here, it's necessary to define the notion of equivalence of such bases. We say that two bases are equivalent if there is some automorphism of Lie algebra under action of each the vectors of the first basis. We have two bases, this one and this one. We say that it's two bases. Oh, I'm sorry, my writing. Next problem. I tried to find my writing. Okay.
Do you want to change the page? You want to go to the next page?
No. I have a problem with my pen. Okay, I try to write with my finger. I hope it works. There is a some automorphism, which some automorphism okay, that phi od ei is collinear to some basic vector of the second basis. In this case, we say that two bases are equivalent. And a natural question we have, how many non-equivalent bases can be found for some Lie algebra? I am going to speak only about nilpotent Lie algebras because I am going to use some result which concerning only nilpotent Lie algebra. But such question can be asked about any kind of finite-dimensional algebras. Now about examples. I am going to this one. About examples. If we have such algebra where N3 is a standard nilpotent three-dimensional non-abelian Lie algebra. If we take its direct sum, we have a six-dimensional Lie algebra. And it is proved that this algebra has two non-equivalent bases. Maybe later I give some details, but I want now to stress one situation. It is rather easy to construct an equivalence between two bases, but it's very difficult to prove that there are no such equivalence. It's a problem. And now next step. Some years later, in the article of Conte and Rossi, construction of nice nilpotent Lie algebras, it's journal algebra, the following question was asked. Is it true that the number of non-equivalent nice bases in a nilpotent Lie algebra is finite? First of all, I am going to speak about the proof of this conjecture. But previously, I note that the concepts of nice and beautiful bases are applicable to any Lie algebras, not only to nilpotent ones. A basis of this kind can be regarded as a very special case of more general concept, a multiplicative basis. And now some ideas how to prove in this article, it was proved that the sets of non-equivalent bases are at most countable. So it's necessary to prove that the countable base, non-equivalent basis is impossible. How it can be done? Now I'm going to this one, and I explain some ideas of proof. Let L be some nilpotent Lie algebras. In the article which I mentioned before, only nilpotent Lie algebras are considered, and the result about countability was proved only for nilpotent Lie algebras. So my result is about nilpotent Lie algebras too. Some ideas about general cases. I am going to speak about it some later. What we have now? If we have some basis and we want to consider it up to equivalence, we may consider not vectors, but lines. Because all situations are considered up to proportionality. And therefore, from initial Lie algebra, we pass to its projectivization, a space of lines in L. In this case, from basis, we have a set of n points where n is dimension L, which are in general position. Then we have a general linear group. It acts on L, and of course, this action induced the action on pivot L. In the general Lie algebra, GL, we consider the group of automorphisms, which acts on P of L, of course, too. But the orbits of this group corresponds to sets of non-equivalent bases because we consider lines. And next step of consideration is the follows. Let us consider not only not any basis, but what I denote nice basis in the algebra L and its reductionization. We have a subset here, and the action of group of automorphisms gives us the action of this on this set. The orbits of this action is the classes of equivalent nice bases. Now, it's necessary to prove that this subset is some algebraic variety. How it can be done? It can be done with aid of some steps. First of all, we consider pairs where k is a function of I and j from the definition of nice basis. And for any such function, we consider equations which define equivalent basis. It is necessary to make some calculations, and as a result, we get that for any such function, the corresponding set is defined by set of algebraic equations, homogeneous equations of degrees 2 and 3. Here we have to use the definition of equivalence and the condition of proportionality. Then we have a union of all such sets, and we get this set which appears to be an algebraic subset in E of L. And now the final consideration is very easy. We have algebraic group which acts on algebraic variety. There are two variants. This action has a finite number of orbits or a continuum number of orbits. But using the result of Conti and Rossi, we know that continuum is impossible. So the number of non-equivalent nice bases in nilpotent algebra always will be finite. It's the first step. Next step. It is natural to ask how many non-equivalent bases we may find in some nilpotent algebra. For dimension 7, it will be 0, 1, or 2. 0 if we have no nice basis. But I talked about the example from this article, which proved that this algebra has two non-equivalent bases. And this idea may be generalized. Let us consider Oh, I'm sorry, I forgot the main assumption that I consider the Lie algebras over the real numbers. But some commentaries about complex numbers will be some later. We will take the direct sum of such nilpotent Lie algebras, and easy to prove that there are no equivalent p plus 1, p from here, non-equivalent nice basis. And so this number may be as big as we want. It's story about nilpotent algebra, but it's natural to ask what we can do with general algebra. First idea is to consider semi-simple algebras and ask what we can do with k that L is semi-simple. In these Lie algebras is well known some very special basis. It names Chevalier basis. In this basis, the commutators are defined very easy. It's a very natural basis. But unfortunately, this basis is not beautiful because some pairs may give just the same basic element k. Only for SL2, the nature of basis is beautiful. There is a question: is it possible to find a beautiful basis in semi-simple Lie algebra? I have no answer, and I suppose that there are no such bases. Why? My explanation for me is the follows. The Chevalier basis is very natural. It's difficult to imagine that there are some other bases which will be better than Chevalier basis. But maybe I am wrong, maybe. But I think that's a very natural question. And the last object about what I want to speak now is the case of some solvable Lie algebras and a construction of I'm going. Let's consider Lie algebra defined over real numbers. We can consider its complexification. And easy to understand that if L is a beautiful algebra, I mean that it's has some beautiful basis. This basis will give us the beautiful basis in this algebra. So that if this algebra is beautiful, this algebra is beautiful too. And now I have another question. Let L be some algebra of complex numbers. We consider its realification. It means that we consider multiplications or only on real numbers. It's a question. If initial algebra is a beautiful algebra, is it true for its realification? It seems to be wrong because if we have some commutators in this Lie algebra, we may extend it. Oh, I prefer to read here K. We try to extend this basis to the basis of LR. We multiplicate it on the imaginary unit. But unfortunately, its commutator is proportional to this one. So if we try to extend this, we have no beautiful basis. And the result which I want to formulate is the follows. Let us consider Lie algebra. R2 is two-dimensional solvable Lie algebra. Let's consider it over C. Let us consider nilpotent Lie algebra, complex nilpotent Lie algebra, and I'm sorry, two. All this nilpotent Lie algebra, it's semi-simple, it's solvable Lie algebra. And all of them are beautiful. It's very easy to check up. And the question, what we can say about its realifications? The answer is the follows. In all three cases, its realification has no beautiful basis. So from complex numbers to real numbers is very difficult. It is rather easy to prove, but it's necessary to consider all bases in such Lie algebras. Because, so for simple solvable Lie algebras, the idea to investigate the notions of nice and beautiful bases, for me is very interesting. I think I stopped here. Maybe you have some questions.
Thank you very much. Other questions?
Hello. I have one question. Can you hear me? Yes.
Yes, I can.
Yes.
Yes. Okay. Perfect. So my question is the following one. Assume that we have some Lie algebra and we have some nice basis of this Lie algebra. Will it help us somehow to find out all automorphisms of this algebra?
I'm sorry. Once again, please.
We have an algebra with nice basis. Yes.
Okay.
It's Lie algebra.
Yes. Then.
It can be, for example, nilpotent Lie algebra, or it may be not nilpotent Lie algebra, as you wish. And so we would like to describe the group of automorphism of this algebra. Will this basis help us somehow and make it very easy to find out this automorphism?
In some sense, of course, yes, but only in some sense, because the investigation of groups of automorphism of nilpotent Lie algebras is extremely difficult problem.
Yes, but I mean this. So the fact that if we have some nice basis will not.
Yes. I have no idea about this now, but I suppose that it may give some good, some help to investigate these groups, but I have no idea about it.
Do you mean the matrix of the automorphism will have some nice form?
Yes, because we may write the groups of automorphism, but the question was about how can we describe algebraic structure, I think.
Well, algebraic structure or anything, I mean, not necessarily algebraic structure. I mean, I'm more interested in generators of this group of automorphism and the explicit description how these generators act on.
Of course, it may be write down. Of course, it may be write down, but it will be many formulas, and I don't know how to use this result. It's easy to write down the some equations for this group of automorphism, but I don't try. I don't have idea about it now. It's maybe it will be useful. I don't know.
Okay, thank you.
Yeah. Thank you for the question. There's another question in chat. It's about Leibniz algebras. Could this result be transferred to Leibniz algebras? So the result that you have reported, can they be?
Excuse me.
Yes.
The sound is rather bad from you. Maybe
yes. Sorry.
In some direction.
So the question is, what can you say about Leibniz algebras?
Which one?
Are the result? Yes.
Leibniz.
Leibniz algebras.
I'm a strange man. I like Lie algebras very much. And I know that I have one article about Leibniz Lie algebras, but it's first and the last my paper in the direction. Of course, this idea may be used in any classes of finite-dimensional algebras, any. And I suppose that it may be possible to find a rather interesting result for any class. Associative, Jordanian, so on. But my hobby is Lie algebras.
Okay, so I see. Thank you. More questions? Okay, so we thank Vladimir once again, and so we gather next week. Maybe some of the participants will be on the workshop. So